Okay, the last project you did focused on all the scientists that discovered the different parts of an atom. This chapter is focusing mainly on the electrons in atoms because the electrons are what really cause the chemical behavior that you see during a chemical reaction. Let's move on.
In 1913, a Danish scientist by the name of Niels Bohr improved upon Rutherford's model of the atom. While Rutherford proposed that negatively charged electrons were held in orbit by the positively charged nucleus, he did not describe the location of the electrons. Niels Bohr proposed that electrons move in orbits around the nucleus, and he proposed that these orbital paths, or energy levels, are located at various distances from the nucleus. Today, we refer to Bohr's theory as the Bohr model of the atom.
All right. The energy levels in atoms were first discussed and discovered by Niels Bohr. Niels Bohr was a physicist that happened to be the student of Rutherford that developed a new model from Rutherford's model, as you see in the upper right-hand corner. The problem with Rutherford's model is it could only explain a few properties of the atoms, and it could not explain any chemical properties, and that's what we're really interested in chemistry. So what Bohr did was he changed Rutherford's model to incorporate new discoveries about how energy of an atom changes when it either absorbs or emits light, something that Rutherford could not explain. So now, what makes Bohr's model different from Rutherford's is Bohr has these things that we call energy levels. There are areas where you can find an electron. So you look at the example on the right, the nucleus is in the middle, and the black dots, which are indicating the electrons, are in these different orbits. Now, the amount of energy that's needed to move an energy electron from one level to the next is called a quantum of energy. And the very important thing is Bohr said that the electrons have to be on energy levels. They can't exist between energy levels, sort of like your foot can't exist between the rungs of a ladder. The energy levels are unequally spaced. If you look at this picture, they almost kind of look concentric and evenly spaced, but that's not really how they are. They're actually less evenly spaced than you would see. So on the right now, we see electrons at n equals 1, which is the first energy level, and it's absorbing so much energy to go from the first to the third. That would be 2 quanta of energy. Then you see on the top, you see the red photon, which is energy absorbing, is going to then kick it from the second level to the third level. But the problem is when electrons move up levels, they don't stay there because they're unstable. So let me show you this little model here. If you have an electron, it could be in levels 1 through 7. The bottom level is called the ground state. So this electron is a n equals 1 ground state electron. It's absorbing energy, h nu, and it's going to absorb enough energy to kick it from the first to the second. That's called a transition. But the transition causes an excited electron, which is unstable, and what it wants to do is fall back down. As it falls back down to the original ground state, it gives us the same amount of energy absorbed, comes out as a color of light. So let's see a different one. We're going to start at the ground state of 1. We're getting higher energy, h nu, and that higher energy causes the kick from the first to the third, different transaction. So it's going to be an excited electron and fall back down. And what happens when it falls back down? It's going to drop to the ground state, giving off the same amount of energy that it absorbed. And if you learn about light, you'll learn that red is lower in energy, where violet is higher in energy when you talk about visible light. Okay, in 1926, Austrian physicists, going across the screen, Erwin Schrödinger devised a mathematical equation that described the behavior of an electron in a hydrogen atom. This furthered what Bohr did to turn it into a mathematical model. Well, the mathematical model that they use is called the quantum mechanical model. In the upper right-hand corner, you see calculus equations of Schrodinger's equation. It's a lot of math, but they have simplified it for people below calculus students to be able to understand how it shows where the electrons can be in an atom. So, like the Bohr model, the quantum mechanical model restricts the energy of electrons to certain values, certain energy levels. But unlike the Bohr model, it does not specify an exact path that the electron can take around the nucleus. So, the QM model. It shows the probability of finding an electron in certain space surrounding the nucleus as a fuzzy electron cloud, as you see in the upper right-hand corner. The cloud is more dense where the probability of finding an electron is high. In this area, they took from an atomic orbit and they changed it to what's called an atomic orbital. Each energy level is designated by a principal quantum number, n, where n equals 1 through 7, which are the 7 energy levels that an electron can exist in an atom. The energy levels are made up of 4 sublevels. They are made up of atomic orbitals s, p, d, and f. Now, the way that it works is there's 1 s orbital, there are 3 p orbitals, 5 d orbitals, and 7 f orbitals for each sublevel. Each type of orbital has a different shape due to Schrodinger's equation. For example, the s orbitals, which is the yellow sphere. The first set of equations will show you that when you are in an s orbital, you will have a spherical shape, and that's the area where you can find electrons. The p orbitals, there are 3 of them. They're either dumbbell shaped or hourglass shaped. Those are the blue ones. There's 3 of those. The d's are mostly cloverleaf shaped because if you look at the first 4, they're cloverleafs in different directions. The last one is not the same. And the F's are just what we call complex. There are 7 of those, and they come from Schrodinger's equations, and using Schrodinger's equation and you graph them, these are the shapes you can get. These are the areas where you can find electrons. Now, we're not going to use calculus. We're not going to use Schrodinger's equation. We're not going to use these graphs. What they have come up with is a simpler way to deal with this. Now, what they did was, instead of using calculus, they came up with some principles that you could graphically see how the electrons fill. If you look at the periodic table, it's numbered 1 up to 118. Well, those are the different elements that are there. If you look down the left side or the right side, you see the numbers 1 through 7. I just told you those are called the principal quantum numbers. Now, the first rule of putting electrons where they're to be is called Aufbau. It's German for alphabet. And what it says is you're going to fill electrons from lowest to highest energy. So the way it works is you start at hydrogen, and there are different areas which we're going to learn. And those different areas will be the S, the P, the D, and the F. Now, when I show you this, they're going to be in different colors. So as it fills, and all we're doing is counting from 1 to 118, it fills in this order. So basically, I'm just going left to right, top to bottom. And you're seeing all these numbers and letters. And I'll just let it fill. And then I will explain to you how this works. When you first look at it, it looks impossible. But the more you do, the better you will get. And the best part is you never have to memorize this. This is called the Aufbau orbital filling levels. So if I start at number 1 and go up to 118 in numerical order, I will have what's on the top there, which is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, and 7p. Whoa, what is that? Well, that is merely going from helium or from hydrogen all the way to the last element. Now, if you look at it, you can see that I kind of have them split. And I have them split because those are the different rows. If you look in the first row, the only thing you see is 1s. You look in the second row, on the left side you have 2s. On the right side you have 2p. And then the third row you have the 3s. And then on the right you have the 3p. And then the 4s followed by the 3d, then the 4p. So you can see it if you look above that really all we're doing is going from 1 to 118, left to right, top to bottom. So what does this Aufbau say? What it's saying is when you're filling the electrons in any atom, they have to be in a certain area. All of Schrodinger's equation showed you this, but they have now got it down to a simple number and letter designation. So we're going to be talking about what we just started with the 1s and the 2p and the 3d, and it is going to be a way that we call them electron configurations. Before I start, I'm going to tell you that it's kind of nice because the electron configurations are on your periodic table. You will be downloading a periodic table which you're going to be using a lot. So we want to talk about the arrangement of electrons. Why do we want to talk about that? We want to talk about that because depending on where an electron is, it has a certain amount of energy. So on our periodic table and in your notes, there is a table and it has the sublevels, the S, the P, the D, and the F. Next to that is their location on the periodic table and the number of columns, which is going to be a little important. The S, if you would look at the animation I just showed you, were all red and they were all on the left side except for helium. And then the P, they were on the right side and it was 6 columns wide. The D is what we call the middle, the sunken section, and it is 10 columns wide. And the F, which is the bottom of your periodic table, is 14 wide. Now the number of orbitals for S, there's 1, P, there's 3, D, there's 5, F, there's 7. 1, 3, 5, 7. Now, if I double each one of those, 1 doubled is 2, 3 doubled is 6, 5 doubled is 10, 7 doubled is 14. So you're starting to see that this pattern is a very common pattern or a very succinct pattern. Now, the number of electrons per orbital, the rule is you're allowed 2 electrons in an orbital. Well, if I have 1 orbital, 1 times 2 is 2. If I have 3 orbitals, 3 times 2 is 6. 5 orbitals, 5 times 2 is 10. 7 orbitals, 7 times 2 is 14. So I started with the position and the number of columns, and that's going to equal the maximum number of electrons in those orbitals, in those sublevels. Now the shapes, which we just went over, the S is spherical, the P is a dumbbell or an hourglass, the D is cloverleaf for the most part, except that crazy one at the end, and for F we just call those complex. All of those shapes came from those equations that Schrodinger did. What we're doing is we're taking those equations and making them simpler by showing where they are on the periodic table. We just tell you what their shapes are. So here's another periodic table. And you look at it and I see some gray areas and I see that the table that Mr. Freeman has created is different from most that you see in textbooks. If you look at it, you see that there is 2 columns on the left. And if you look at the bottom, that's the S sublevel. But next to hydrogen, you see that there's a block, but it is not assigned to an element. What it should be is helium, because helium is in the first level and it should be on the left side of the periodic table because it has 2 electrons in its orbital, just like beryllium, magnesium, any of them in the second column would have. But also notice that I have it separated from rows 2 through 7 on the right because it's not in the same sublevel as them. Those would be considered the P sublevel. The S sublevel is columns 1 and 2, 2 electrons high. The second set is P. I told you that P was 6 columns. If I go from 13 to 18, that's 6. So that's the P sublevel, which is columns 13 through 18, which is the maximum of 6 electrons. And then notice in the center, if you go from 3 to 12, that is that considered the D sublevel, and that is 10 electrons because it's 10 columns wide. And on the bottom, we see if I count from left to right, I go 14 columns. And those 14 columns are the F sublevel. So I've created a periodic table that actually splits the sublevels. So you can see the gray ones and helium are in the S. The whole sunken section in the middle is the D. The right side from rows 2 through 7 is the P, and the bottom 2 rows are the F. So I'm trying to do this, and you can also see on the periodic table up top that I have that animation that I showed you there. I just have the ending so you can see the S, the P, the D, and the F. So now, why would we want to know this? Well, we want to know this because we want to figure out where electrons are, because those electrons are going to dictate the types of reactions that different elements go into. Now, electrons that are in the ground state, remember, ground state is when the electrons are stable in the lowest possible areas. So the first rule is called Aufbau, which I went over. And the Aufbau says electrons fill orbitals of lowest energy first. So since 1s is listed first, well, that's the lowest energy level. It's the first level, S sublevel. The second level is the second S and the second P. Then the third is 3s and 3p, and 4s and 3d and 4p. You'll notice I have them broken up by their rows because that's the row that they're found in. If you look at the bottom of the periodic table that I gave you, this Aufbau principle is listed there for you. There's no need to memorize, and once I show you how electron configurations are done, that they're all listed on your periodic table. The second rule for electron configurations is electrons want to be spread out as far as possible. So Aufbau starts by putting them in different areas. Hund's is the second rule that says when they fill equal energy orbitals. Now that doesn't apply to the S because the S only has one, but applies to the P, which has 3, the D, which has 5, and the F, which has 7. So when you're trying to fill those equal energy orbitals, the electron is always going to enter each orbital one at a time. So since the P has 3 orbitals, the first 3 electrons are going to fill that first orbital, then the second orbital, then the third. You can't basically put them together until they are all with one electron, keeping them as far apart as possible. The Pauli exclusion principle shows that each orbital can hold 2 electrons, but if they're paired, they have opposite spins. And I'm going to show you how this works. If we're writing electron configuration, and I want to write it for tin, I find on my periodic table tin is number 50. So when I'm doing this, I want to figure out how will I fill it. So in order to figure that out, I use Z, which is the number listed on the left and bottom. That's the atomic number, and that's going to be equal to the number of electrons. Then I use the Aufbau order, 1s, 2s, 2p, up to 7p, as listed there and on the bottom of your periodic table. The rule is, until you run out electrons, you fill all the s's with 2, all the p's with 6, all the d's with 10, and all the f's with 14. And only the last sublevel can be a different number than that. So if I do 10 and I start it over. So I want to go to 10 and I want to go backwards. So I have 1s up to 5p. Now, how did I know to write those numbers? Well, I look on my periodic table and I find tin. Tin's on the right-hand side. It's in the 5th row on the right side. Well, the 5th row is a 5. The 5th row up top, there's 5s, 4d, and 5p. Since it's on the right, I know that it's going to be a 5p because the p is the right side. So now I'm going to fill it. And every one of them, the s's get 2s. The p's get 6s. The d gets 10. And I stop. I stop at 4d because the only one that can be different than those is the last one. So if I count 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2 plus 10, that's equal to 48. 2 and 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, 30 plus 6 is 36, 36 plus 2 is 38, 38 plus 10 is 48. So 48 from 50 is 2, so I'm going to put a 2 there because that gives me a total of 50 electrons. Now I'm going to do the same thing for zinc, but I'm cheating here a little bit. Since zinc is 30, I look above at tin and I fill everything up to 4s with the 2s and the 6s. Why? Because every element has to follow Aufbau. So I'm going to do this. My 1s gets 2, my 2s get 2, my 2p gets 6, my 3s gets 2, my 3p gets 6, my 4s gets 2. Whew. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20. So 20 from 30 is 10. So guess what? I'm going to put a 10 there because 10 plus 2 plus 6 plus 2 all the way back is 30. Now I'm going to do rubidium, which is 37. So I'm going to do my first ones. Keep going, keep going, keep going, keep going. Now, I know that it's 5s because when I find number 37, it's in the 5th row on the left side. Then I ask myself, which column is it? Column 1 or column 2? Well, let's do the math again. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36. So 36 from 37 is 1. So it's going to be a 5s1. Now, before you panic, let's do this a little bit different. I start and I find my element. So look on your periodic table for tin. When you find it, it's number 50, so that'll help you get there. Notice you're in the 5th row on the right side, which is the P sublevel, and the second column in. So you could really do this a lot simpler by writing the set of 1s, 2s, 2p up to where the area is, and then just look at how many columns from the left you are. So when I do tin, the last one's 3D because it's on the right side of the 4th row, and the middle of the 4th row is 3D. So that becomes the 10. And if you don't believe me, count them. Same thing, rubidium. It's in the 5th row on the left side. It's in the first column. That's why it's 5s1. Now, the noble gases are special. Group 18, and you see the picture there of the excited gases. And they basically take the gas, they put it in a tube, they eliminate all other gases, they throw electricity through it, and they give off those different colors. And they're special because the noble gases comes from the word Edelgas, which first used to indicate their low reactivity. They're also were called the noble gases, and they're also called the inert gases. That, like I said, Edelgas means like inert or idle, not doing anything, and noble is because every element wants to be like these electrons, these elements that have these specific sets of electrons, which we call complete full shells. If you look at the electron configurations I have, helium is number 2, so it's 1s2. Argon is number 18. So whoa, wait a minute. What is this neon 3s2, 3p6? What is this argon 3d10, 4s2, 4p6? Well,
here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just light. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
Now, they are, okay, The noble gases are special in the fact that they have completely filled shells, which means they're the last element of that row, of that period. Because of that, they are very stable. And when they're stable, those electrons aren't going to do anything. So if I look at tin, so I go to my right, I go down to 50, I see Sn, which is tin. I notice that I'm on the right side in the fifth row, so it's 5p. But if I write it out, I have all those 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2, which we did before. But the only electrons I'm interested in are the ones in the fifth row, which is 5s2, 4d10, 5p2. Well, if I add those together, 2 plus 10 plus 2 is 14. Well, tin's in the 14th column. So that's basically the electron configurations are telling you where you are. I'm in the 14th column of the fifth row. Now, what about this fourth row and the third row and the second row and the first row? Well, those are stable. They have every one of their orbitals, every one of their sublevels is full. So what I can do is I can now write that as what element is at the end of the fourth row? Well, the element krypton, which is the noble gas before tin, is number 36. Well, that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 is 36 electrons. So instead of having to write all of that from 1s to 4p, I just put the symbol Kr, which is krypton, in brackets. Those squared brackets tell me that that inner electron shell, the 4p6, the fourth energy level, is completely filled up to krypton. What it is not filled in is the fifth row, because the fifth row doesn't go to 16, it only goes to 14, because 2 plus 10 plus 2 is 14. So what I do is I take that 1s2 to 4p6 and I turn it into Kr, because that means it has 36 inner electrons and 14 outer electrons. I can do the same thing with zinc. Zinc is in the fourth row. And if you do 2 plus 10, that's the 12th column. So instead of having to write 1s2, 2s2, 2p6, 3p6, we're going to then say that argon, which is number 18, which is the noble gas before zinc, that will be Ar and then 4s2, 3d10, because that's the fourth row, the 4s and the 3d. The 4s and 3d, 2 plus 10 is 12. I can do the same thing with rubidium. Well, rubidium has 4p6 just like tin, and then 5s1. So I'm in the fifth row again. So I'm going to have the same inner core, which is the krypton core, and then 5s1, which is krypton is 36 plus 1 is 37. So if I look at these condensed, compressed electron configurations, I now can see the electrons I'm interested in. We're really only interested in the electrons that are on the outermost level, because those are the ones that are exposed to be able to be used for chemical reactions and bonding.
Sheldon, I know you're in the zone, but do you want some tea? All right, I can't believe I'm going to say this, but you haven't spoken in hours, and I'm starting to get worried. Please say something.
Leonard, prepare to be humbled and weep at the glory of my genius.
Nope, it was better before.
Look at it. I feel like my mind just made a baby. And it's beautiful. It's not like human babies, which are loud and covered in goo.
Holy crap, Sheldon. Did you just figure out a method for synthesizing a new, stable, super heavy element?
Did I? Well, that can't be right. No one's ever done that before. Except me, because I just did it! Sheldon and his brain, yeah! 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 Sheldon and his brain.
Now, the reason I show you that clip is because when I saw this this episode for the first time, I was looking at the electron configurations. So what I did as soon as it was available is I found it, I paused it, and I looked at the work. All of the electron configurations that are in this clip are actual electron configurations. After I found this out, I started doing some research and found out that The Big Bang Theory had both a physicist and a chemist on staff to write all the whiteboards. So all the equations that you see are actual equations. Now, what is this? This is so much here. Okay, so let me see. If I look on the left side, orbital filling sequence, that's Aufbau. And then I see 1s, 2s, 2p, 3s. Oh, so basically what they've done is they've taken the Aufbau principle and put it vertical instead of being horizontal, written as we've done so far. So what we're going to do is we take that vertical increasing energy line, and now we're going to make it two-dimensional. The 1s, 2s, 3s, notice there's one box. Well, that's because the s sublevel has one orbital. And then I look at the p's, 2p up to 7p. There's 3 boxes. That's because there's 3 orbitals. The d has 5 boxes because there's 5 orbitals. And the f has 7 boxes because there's 7 orbitals. And then let's go through this. The s orbital, each orbital holds 2. 2 times 1 is 2. 3 times 2 is 6. 5 times 2 is 10. And 7 times 2 is 14. So if you put 2 electrons in each box, you're now fulfilling this Aufbau orbital setup. So what does each box diagram represent? It represents an atomic orbital, which is an area where you can find electrons according to the quantum mechanical model. How many electrons can each orbital hold? 2. Because they said the most that any electron orbital can hold is 2, and if they're together, they have to have what are called opposite spins. I'll explain that in a moment. How many electrons can the d sublevel hold? Well, it has 5 orbitals, and there's 2 electrons per orbital. 5 times 2 is 10. Now, which is associated with more energy, 2s or 2p? Well, it says increasing energy goes from the bottom up. I always equate this to filling a glass with water. It always fills from the bottom up. So then I look at the diagram and I see the 2s and I see the 2p, and the 2p is just slightly higher. And you can tell by looking at the hashers that are coming off the outside boxes that the 2p is just a little bit higher. So that would be higher in energy of 2p versus the 2s. Now, which is more energy, 2s or 3s? So then I look at the diagram, and at the diagram on the left, the 3s is above it, so the 3s has higher energy. According to the principle, which is filled first? Well, it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d. So the one that would fit first is the 4s. Which has the least amount of energy? That would be the one at the bottom, which is the 1s. Do not ask me why they gave you 2 lines to write 2 symbols, but that's where it was. What is the likelihood of finding an electron in the 1s orbital? 100%. It's always the first one filled. According to the Aufbau principle, 1s is always filled before any other orbital. Sequence them in order they should be filled according to the Aufbau principle. Well, if you look at the bottom of your periodic table, or you go back to the diagram that was on the previous slide, or you look at it on the paper, it was 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f. Right off the bottom of your periodic table. And a general rule for describing filling orbitals, Aufbau always fill lowest energy first, which if you look at the bottom of your periodic table, it goes left to right. If you look at the diagram, they just took that and put it on the 1s end. Now, sometimes using Aufbau is incorrect. And these are called exceptions. Using Aufbau can be incorrect for certain elements in the D sublevel or the F sublevel. So we're going to look at numbers 24 and 29. Well, number 24 is chromium, like chrome wheels. And if I write it Aufbau, I go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. because that's 2, 4, 10, 12, 18, 20, 24. Same thing with copper, which is 29. So I go, everything's the same up to 4s, and then that's 20 plus 3d9 is 929. That's what you would think. But when you look at chromium and you look at copper, you'll see that it's not 4s2 3d4 or 4s2 3d9. It's 4s1 3d5 and 3d10. The reason they do this is a half-filled 5d orbital or a complete filled 10d orbital is more stable. So what happens is one of the electrons from the 4s, which is lower in energy, gets moved up. It migrates. It is given a higher energy level. And what that is because you've got more electrons in an area and they're stronger. So what they can do is pull that 1s electron out of there to make it a 4s1 3d5 or a 4s1 3d10. And that makes the D sublevel more stable. Now, I'm going to show you the exceptions. Chromium, copper, niobium, molybdenum, ruthenium, rhodium, palladium, silver, platinum, and gold. And the two new ones that were just recently created. Now, if you notice, they are different on your periodic table because their electron configurations are blocked out in white. And you'll notice that the rest of the electron configurations, they're there, but they're just written. Well, what I did was I tried to show you where the exceptions are. And it's really weird because if you look especially at column 11, copper, silver, and gold are some of the most well-known elements in the world. And they all are exceptions. And then you look at the 4D sublevel. Other than yttrium, zirconium, technetium, and cadmium, all the rest, those other 6, are exceptions. And it's kind of odd because I always think about this. If you think about the periodic table, there are only really 92 natural elements. And the ones around that area are the ones that are exceptions, which is kind of odd. And the same thing with platinum. And if you look at chromium, those are the 4th column. So 2 of them in the 4th column are exceptions, where all of them in the 11th column, which is the 9th column of the D sublevel, are all that way. It's just for stability.
In the modern theory of the hydrogen atom, or any one electron ion, all subshells with the same principal quantum number n have the same energy. Theory tells us, however, that in atoms containing more than one electron, the repulsive interactions of the electrons with one another cause subshells of the same principal quantum number to differ in energy. The one electron in the hydrogen atom, in its lowest energy, or ground state, occupies the 1s orbital. In helium, atomic number 2, there are 2 electrons. Where does the second electron go? The first rule is that electrons occupy the lowest available orbital. The second rule follows from the Pauli exclusion principle. Any orbital can hold at most 2 electrons of opposite spin. These rules tell us that in helium, both electrons occupy the 1s atomic orbital. With increasing atomic number, the electrons occupy orbitals of increasing energy. With carbon, we encounter a new question. Because there are 3 degenerate 2p orbitals, that is, orbitals of equal energy, Hund's rule tells us that with 2 or more orbitals of the same energy, we should place electrons singly in each, with parallel spins until all are half full.
Now, if you look at this, and it's a little blurred, but you'll see that what they're doing to indicate the electrons are they're using arrows. The first arrow always goes up, the second arrow goes down. That's indicating the electrons have what we call opposite spins. One is spinning clockwise, one spinning counterclockwise to keep the electrons as far apart as possible. So when you're looking at these, on the right, underneath the 6 electron blur, you see 1s2, 2s2, 2p2. But on the right, you see 2 arrows in the 1s, 2 arrows in the 2s, and 2 arrows separated in the 2p. All of that is basically to show what you need to do electronically, and you can only show that using an energy level diagram. When you're just using the Aufbau principle, which is listed underneath the white box, you really can't tell if they're following the Hund's rule.
With nitrogen, we arrive at a half-filled subshell. A half-filled subshell is associated with special stability. As we come to oxygen, having used up all the vacant 2p orbitals, we must pair electrons. With neon, we come to the end of the first row of the periodic table, and the stable octet of electrons in the outermost shell.
Now, if you look at neon, it's 1s2, 2s2, 2p6. If you look at the diagram, you see that each one of the boxes, which is the orbitals, has 2 electrons. One is counterclockwise and the other one is clockwise, which we call one up, one down. So as I look at each one, the 1s2 underneath the white box is equal to the 2 half arrows in the 1s block to the right. Then the 2s that has 1 block, the S2, you get 2 electrons. 2p6, you'll notice there's 3 pairs, each of them going one up, one down. And that is how you can show Hund's rule, Pauli exclusion principle, and the Aufbau. Now we're going to practice these. So we don't do a lot of these because they take up a lot of space. If you look in your notebook, there's only 4 of these on one page. And because of the size of the page and what it takes, I couldn't even put boxes. So in your notes, you just have a line. Well, the line indicates a box. The box indicates an orbital. So if you look at it, once again, it is an increasing energy, which is Aufbau, which is 1s all the way up to 6p in this case. So I can, when I want to do an element, all I have to do is write out the electron configuration and then fill the boxes. So I'm going to show you. We're going to start with a large atom, lead. So the first thing I do is I look and I see the number to the left is an 82. So what that means is I'm going to have 82 half arrows in this diagram. Now, since we want to work smarter, not harder, the first thing I'm going to do if I want to do... All right, so I want to write this out. So the first thing I'm going to do is I'm going to write out the electron configuration. So what I want you to do at this point is I want you to write the electron configuration either as the complete electron configuration or as an Aufbau configuration. And that shows what you're going to do. So please pause the video and do that now. Now that you've written both the expanded and the condensed electron configuration in Aufbau order, we're going to put them into the diagram. So first thing I'm going to do is I'm going to put the first 2 in the 1s. 1 arrow up, 1 down. That's showing opposite spins, fulfilling the Pauli exclusion principle. So that takes care of the 1s2. Then I'm going to do it for the 2s. First arrow goes up, second arrow goes down. Then I'm going to do it for the 2p. First arrow goes up, but since they're equal energy, the second arrow goes in the second, the third arrow goes in the third. You want to do that to fulfill Hund's rule. Now, if you're filling this completely because it's a 2p6, I'm not going to see you not following Hund's rule, but do realize that Hund's rule is only ever seen in the uppermost electron orbitals, and that in this case is 6p. So when I write my 6p, that's when I have to worry about it because everything below that is going to be filled. Whoa, how did I do that? I know it because I look at the electron configuration and I see 6p2. Well, that means everything before that has a 2, a 6, a 10, or a 14. So I'm going to work smarter, not harder. And I'm going to fill everything up to the 6p. And now I have 2. So the first electron goes in the first box. The second electron goes in the second box to make sure we fulfill Hund's rule. And remember, the only place you're going to see that fulfillment is in the last orbital. Now, if it's an s orbital, you're not going to see it because there's only 1. But if it's a p sublevel with 3 different orbitals, you have to make sure until you hit 4, they're all singles. Down the right side, I want you to write Aufbau because that is showing Aufbau. It's basically, like I said, filling a glass of water from bottom to top. The second thing I want you to do is pick out 2 of the orbitals and put some arrows to them and say Pauli exclusion principle. So really, every single one of those red boxes, which are the orbitals except 6p, is fulfilling the Pauli exclusion principle, which says if they're in the same orbital, they have opposite spins, which keeps them as far apart as possible. And the only one I want you to write is underneath or above the 6p. I want you to write Hund's rule, because Hund's rule says that if you're filling equal energy orbitals, that's the p's, the d's, or the f's where there's multiple, if you're filling them, you must have one electron in each orbital before you can have a pair. So in order for this to be having the electrons as far apart as possible, I put 2 electrons both facing up in separate squares, which are separate orbitals. That allows me to see all 3 rules. And that's why we do these, is because you can now see that in the 6p, I have 2 electrons, they're unpaired, and that's going to come into effect when lead forms its ions. Now, I want you to do number 39. Now, I've already written it in up to 5s2. Why? Because I look at the electron configuration, which you should write. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 41, or krypton 5s2, 41. Write those now and fill all the electrons up to 5s2. Pause the video. Okay, now that you're back, the only sublevel that doesn't have an electron is 4D. You'll notice there's 5 empty boxes there. I only have 1, so guess what? I'm going to take that 1 electron, place it in the first box, which then fulfills the Aufbau principle. And if you don't believe me, there are 39 arrows on there, because 2 plus 2 plus 6 is 10, plus 2 plus 6 is 18, plus 2 is 20, plus 10, 30, 30 plus 6 is 36. 36 plus 2 is 38, plus 1 is 39. Pause the video at this point, writing the electron configurations, and do the last 2. Pause it. Now, I want to go over germanium. At this point, if you did what I asked, you have the electron configuration, you have both the regular and the condensed, and you're all the way up to 3d10. Now, when I go up to 3d10, now you'll notice on your electron configuration that goes 3d10, 4s2, 4p2 for germanium. That really doesn't matter. The main thing is that 4p is last, because what your electron configurations on your periodic table do is they put them in numerical order, because even though 3d10 has more energy than 4s, it's still the 3rd energy level. So I have everything up to 3d10. So I look at my 4p, I have 2 of them. 1 goes in the first box, 1 goes in the second box. That is to fulfill Hund's rule. All the other ones are completely filled because of Pauli exclusion, and they're filled up to there because of Aufbau. Now I told you to do the other one. If you have not, at this point, pause and do the last one. The final one is rubidium. Rubidium is krypton 5s1. So the krypton is the end of 4p. So from 1s to 4p are completely filled. That takes care of 36. And that last electron comes moseying over to become a 5s1 right there. If you don't believe me, count all of them, and you will have 37 electrons. Now, as I said, orbital energy diagrams or energy level diagrams or Aufbau diagrams, whatever you want to call them, they are not used except when you're trying to see Hund's rule, Pauli exclusion. If you just want to see Aufbau, you're just going to see that what you see in the bottom right, the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Now, electron configurations for every element are already done for you on your periodic table. The main thing here is I showed you the elements and I showed you the rules so you understand how they get where they are. But it is not important in my thoughts that you have to know how to do them, and that's why I put them on the periodic table. So you just find the element, find the electron configuration, because now we're going to do some work with it. Our first lab that is coming up is going to deal with the electron configurations of ions. And before we do that, we kind of have to do a little background. When you look at the periodic table, I have this in 3 different areas. I have the green, I have the yellow, and I have the orange. Well, the green ones are indicating all of the metals. Metals make up about 80% or more of the periodic table. Then you see that staircase of B, S, I, G, E, A, S. That's called the area of the metalloids. They're not quite metals, they're not quite nonmetals. And then the orange ones I have listed as the nonmetals. Now, very important, when you're forming an ion, metals are going to lose electrons because the way that they're set up, it's easier for them to lose electrons to become more stable. Nonmetals are going to gain electrons because in order for them to get more stable, it's easier for them to gain. And it all depends on their electron configurations of why this happens. Well, when we're trying to do electron configurations of gaining or losing, we have to do a little bit of background. When they form ions, what's going to happen is atoms will gain, which is the nonmetals, or lose, which is the metals, electrons to have the configuration of the nearest noble gas. Now, I told you before, the noble gases are special, and they're special in the fact that they are stable. In order for metals or nonmetals to become stable, they do this by either gaining or losing electrons. Now, transition metals are the ones in the D sublevel in the center. Now, they're going to lose electrons first from their S and then from their D. So the first electrons any metal will ever lose is their S electrons, which are the ones on the left-hand side. Once they lose those S, then they can form the D, or I should say lose D electrons. And if they're just a regular metal, they could also lose their P electrons. Now, when you're doing this, I'm going to give you some examples. Now, I have listed aluminum as neon, 3s2, 3p1. And then I have aluminum, which forms a +3 charge. And you'll say, what do you mean it forms a +3 charge? Well, the nearest noble gas to 13 is 10. So the way to get back to 10 is lose 3. So if I have $13 when I leave and I come home with 10, I lost $3. So if I look at this, you can kind of see that neon 3s2, 3p1, that 3s2, 3p1 is a total of 3 electrons. So watch how this actually happens. When aluminum becomes the ion, I'm going to lose my 3s2 and my 3p1, which leaves me with neon, which is a noble gas. The same thing with strontium. It's Kr5s2. Well, guess what? Strontium to become +2 is going to lose that 5s, 2 electrons. And guess what? Now I go from 38 down to 36, which is krypton. Anions are the opposite. They will gain to go to their nearest noble gas. So I find sulfur. It's number 16. I write its electron configuration. Neon, 3s2, 3p4. Now, when it forms its anion, which is called sulfide, it's going to gain 2. So the negative is what always gets people because they're saying it's a negative charge, but it gains. Well, it's gaining electrons, which are negative. So it's going to go from 3p4, the maximum for p is a 6. So watch how I go from sulfur to sulfide. The 4 goes and a 6 comes in because the nearest noble gas to sulfur is once again argon, because it's number 18. So sulfur has 16 electrons, but sulfide has 2 more, which is 18 electrons. Bromine is the same thing. Bromine is number 35. It's bromide, which is Br-1. We don't write the ones if they're ones. That 4p5 is going to go up to 4p6. So now if you look on your periodic table at 4p6, you have krypton, which is number 36. So what happens is when metals lose to form cations, they go back to the nearest noble gas. Anions will go up to their nearest noble gas because the one that's closest to them is ahead of them. Where for cations, the one that's closest to them numerically is back behind them. So what happens to a neutral atom if it loses 1 electron? Well, I just told you that when elements lose electrons, that's a cation because aluminum loses 3. When it loses it, what happens is if you become losing one electron, it's going to become a +1 charge because now it has more protons than electrons. You probably say, whoa, whoa, wait a minute, wait a minute, wait a minute. You have to remember that Eugene Goldstein discovered the proton. J.J. Thomson discovered the electrons. Protons are positive, electrons are negative, and when you're looking at the periodic table, the atomic number, like you look there for, let's say F is 9. Well, that atomic number tells me how many protons are in the nucleus, and then F, if it were to lose one, that would be 8. If it were to gain one, that would be 10. Well, when metals form ions, that would be something like lithium or beryllium or sodium or magnesium. When they lose one electron, they now are positive because they have more protons than electrons. If it gains 2 electrons, it would become -2 because now it has 2 more electrons than protons. The way it works is neutral atoms are equal in their number of protons and electrons, so they balance. When they lose, they become positive because they're losing electrons, which then increases the charge positive versus the negative charge. It's no longer 0. And the same thing here. If you gain 2 electrons, it's going to go from 0 to -2 because now you have 2 more electrons and electrons are negative. A simple word equation to show how you can figure out the charge of an ion is the charge is equal to the protons minus the electrons. If it's neutral, let's say for sodium, 11 protons, 11 electrons, 11 minus 11, 0. But if you have 11 protons and the nearest noble gas is neon, which is 10, protons 11, electrons 10, 11 minus 10 is +1. So lithium or sodium would become a +1 charge. All right. What is the electron configuration of each of the following? In each case, also tell what charge the atom is likely to take on of its bonds and explain why. Write the electron configuration of that ion. Okay, so I have a table here with elements. I want their electron configuration, I want their charge, I want their electron configuration of their ions. So the first thing I'm going to do is I'm going to look on my periodic table and find the elements. Well, beryllium is number 4. So my electron configuration is going to have a total of 4 electrons. When I find beryllium of number 4, I look at my periodic table, I see where it is, it's in the second row, it's on the left side, and it is in the second column of that section. So helium 2s2, or just look underneath at the bottom and you get that. Now the charge, beryllium is on the left side is metal, so anything that ends in S or D is going to, or F is definitely going to be a metal. The only ones that will be possibly nonmetals are in the P sublevel. So since it's an S2, I know I'm going to get to my nearest noble gas. Well, my nearest noble gas to 4 is 2, which is helium. So I'm going to lose those 2 because 4 minus 2 is 2. So now I have a charge of +2 because remember, to get the charge, protons, which is the number 4, that's the atomic number, and I subtract from that the number of electrons lost. So 4 minus 2 gives me a +2. So my electron configuration, if I get rid of the 2s2, is just the helium that was there originally. So now, got to find F on the periodic table. I look, I find it's number 9. So this is on the right side of the periodic table. So this one's not going to lose, it's most likely going to gain because the nearest noble gas to 9 is number 10, which is neon. So I look underneath F, I write out its electron configuration. Okay, the difference between 9 and 10 is going to be -1 because I'm gaining 1 electron. So from 5, I'm going to go up to 6. Now, if you're trying to figure out, well, how are you getting this charge? Well, fluorine has 9 protons. As an atom, it has 9 electrons. But as an ion, it has the same number of electrons as number 10, which is 10 electrons. 9 minus 10 is -1. Argon's kind of special. I look, I find it's on the right side, it's number 18. So I write the electron configuration straight off the periodic table, and it's 3s2, 3p6. The nearest noble gas is argon, so guess what? I don't have to go anywhere. And guess what? I am also not going to form a charge. So if I don't form a charge, my ion and my electron configurations are the same because I didn't gain, I didn't lose. So now I have to find sulfur. Look to the left of argon. There it is, number 16. So what's the difference between 18, which is argon, and 16, which is sulfur? If I take that 3p6 and take 2 away, I'm back to 3p4. See, simple subtraction. I have 2 less electrons. Now, when I have p4, I'm on the right side, I'm in the nonmetals. That means, guess what? I'm going to gain 2 to go back up to p6. But by gaining electrons, remember they're negative, because people go, you just said they gained, but it became negative. Because what's happening is I'm adding negatives. Sulfur has 16 protons. The sulfide ion, if you look at the electron configuration, 10 plus 2 plus 6 is 18. 16 minus 18 is negative 2 because I have 2 more electrons than protons. So then I want to do sodium. I look around, it's on the left side, it's number 11. So I write it out, I look underneath it, I see neon 3s1. Well, the nearest noble gas to 11 is 10, so it's going to become positive 1, and I'm going to lose that 3s1 to have that neon core. Because what happens with metals is they're going to lose. What happens with nonmetals, they're going to gain. So then I have one more to do. Nitrogen, it's 7. So on the right side, well, that means Mr. Freeman said it's going to gain. So I write the electron configuration off the periodic table, and I'm going to see I've got 2 plus 3 is 5. I need to go up to 7 plus 3 is 10. So I'm going to have a negative 1 charge by taking that 2p3 up to 2p6. So if I look at these, every single one of them, minus the helium, ends in p6, because even neon for sodium is the same thing. That's right up above with the helium 2s2, 2p6. They're all ending in p6, except for helium, which ends in 2. The only reason is there's no p sublevels in the first energy level.